We're counting down the 8 most astonishing reasons why Michio Kaku claims that 3I/Atlas could actually stay in our solar system. From upcoming windows that may reveal its ultimate fate, to mysterious properties and debates shaking the scientific world, each entry unpacks a fresh anomaly or turning point in this interstellar saga. Expect surprises, from improbable statistics to bizarre chemistry and unprecedented cosmic blind spots, all building toward the critical moment when everything could change, unseen. Which factor ranks as the most decisive for the future of 3I/Atlas? Let's begin with number 8. The next observation windows that could finally confirm what happens after the blackout. In the 8th place, the countdown begins with the calendar windows that will decide the fate of 3I/Atlas. December 2025 marks the first critical checkpoint. After 6 weeks hidden behind the sun, Atlas returns to the night sky. On December 19th, major observatories like the James Webb Space Telescope and the Vera Rubin Observatory are scheduled to reacquire its position, armed with updated ephemerides and high-precision astrometry. The goal: measure its outbound trajectory to the nearest arcsecond, checking for any deviation from the predicted hyperbolic escape. If Atlas emerges on track, the natural comet model survives another round. But even the smallest orbital shift, beyond the 10,000-kilometer uncertainty envelope, would trigger a scientific firestorm. The next decisive window opens in March 2026, as Atlas passes within 49 million kilometers of Jupiter. Here, gravitational models predict a measurable deflection if the object is still unbound. The James Webb Space Telescope, ground-based telescopes, and the Rubin Observatory will track its path nightly, searching for telltale changes in velocity or direction. These 2 windows, December's reappearance and March's Jupiter flyby, are the final arbiters. Hyperbolic escape means the mystery fades with distance. A captured orbit, on the other hand, would rewrite the textbooks. Until then, the world waits for the numbers to settle the debate. Number 7. The scientific debate over 3I/Atlas erupts into a high-stakes clash, drawing sharp lines between mainstream caution and speculative urgency. NASA's official position, echoed by Karen Meech, Quanji Ye, and Tom Statler, remains anchored in the principle that extraordinary claims demand extraordinary evidence. For them, Atlas's mass, chemistry, and trajectory are outliers, not outlaws. Anomalies, they argue, stretch the boundaries of comet science but do not break them. Internal memos from the Planetary Defense Coordination Office revealed tense exchanges. Risk analysts flag the object's statistical improbability, while comet specialists urge restraint, warning against premature alarm and budgetary overreach. Yet the alternative camp, energized by quantum AI simulations and the vocal presence of theorists like Loeb, insists the stack of anomalies, mass, orbital plane, volatile ratios, justifies maximal scrutiny. Leaked simulation outputs from Kaku's own modeling team, though never formally published, circulate in policy briefings, projecting a non-negligible probability of Atlas shifting into a bound orbit. Competing budget proposals surface, each tied to the object's risk profile and the possibility of planetary perturbation. The intellectual crossfire spills into the media, with every new dataset feeding a cycle of speculation and skepticism. As December's observation window approaches, the debate sharpens. Will the numbers confirm a cosmic visitor, or reveal the first captured interstellar object in history? Number 6. The capture hypothesis distills the entire Atlas debate into a single razor-sharp calculation. At perihelion, 3I/Atlas will skim the sun at nearly 44 kilometers per second, a velocity that, by all classical models, guarantees escape back to interstellar space. But orbital mechanics leaves a loophole. Subtract just 8 kilometers per second from that sun-skimming speed at the critical moment, and the object's path flips from hyperbolic to bound. The physics is unforgiving. Only a precisely timed retrograde impulse delivered almost instantaneously at closest approach can achieve this transformation. The Oberth effect magnifies the impact of any velocity change at perihelion, making it the only window where such a maneuver is even theoretically possible. For a comet, natural outgassing delivers force in the wrong league entirely. Even the most violent jets or fragmentation events impart changes on the order of meters per second, not thousands. Gravitational nudges from planetary flybys, while dramatic in simulation, fall short by orders of magnitude unless chained over years and with near-perfect alignment. The required delta V, 8,000 meters per second, all at once, remains far beyond the reach of any known natural process. Yet the blackout at perihelion means that, if such a maneuver were attempted, every instrument capable of catching the act will be blind. Only when Atlas re-emerges will the numbers reveal whether the unbound visitor has become a permanent resident. The stakes are absolute. A captured orbit would signal either a cosmic accident of staggering improbability or a deliberate act that rewrites the boundaries of planetary science. Number 5. The optical and chemical anomalies of 3I/Atlas pull the story out of the realm of orbital mechanics and into the raw sensory strangeness of this visitor. The earliest images confounded expectations. Instead of the classic cometary tail streaming away from the sun, Atlas revealed a forward-facing glow, a coma brighter in the direction of motion, as if sunlight scattered off a dense reflective shroud. For weeks, the tail refused to form, leaving survey teams to debate whether they were witnessing a trick of geometry or something fundamentally new. When the tail finally appeared, it snapped into place with textbook precision, but the delay left a residue of doubt. Spectroscopy from the James Webb Space Telescope added a sharper edge to the puzzle. The volatile ratio came in at nearly 8 parts carbon dioxide to 1 part water vapor. In ordinary comets, water dominates the chemistry. Here, carbon dioxide rules by a landslide, hinting at an origin in deep interstellar cold, far from any sun's warmth. The numbers did not fit any known solar system template. Then, as Atlas drew closer to perihelion, a sudden surge of green emissions swept through the coma. C2 and CN molecules lighting up weeks ahead of schedule, and at intensities more typical of a comet already in the inner solar system. Emission timing curves plotted by the Rubin Observatory flagged the anomaly in real time, forcing a rewrite of every thermal model on file. Each anomaly, forward glow, carbon dioxide dominance, premature green flash, adds a layer of material mystery. For those searching for a natural explanation, the challenge is clear. Atlas refuses to look or behave like any comet on record. For the skeptics, these physical oddities become the strongest evidence that something about this object is fundamentally out of place. Number 4. The trajectory of 3I/Atlas sketches a path that defies the usual playbook for interstellar visitors. Trajectory maps reveal a corridor almost flush with the ecliptic, tilted by just 5 degrees. A line so straight, it could have been drawn with a ruler, threading through the planetary plane rather than diving in from a random angle. This is not the chaotic plunge seen with Oumuamua or Borisov. Instead, Atlas's approach reads like a calculated entry, hugging the solar system's busiest highways. The sequence of planetary encounters only deepens the puzzle. On October 3rd, Atlas will sweep past Mars at a distance of 29 million kilometers, close by cosmic standards, well within the orbit of Mercury. Weeks later, its path brings it within range of Venus, and then, by March 2026, near Jupiter. Orbital dynamicists have run the N-body simulations. The compounded odds of a massive, high-velocity object threading this exact sequence are vanishingly small. Each flyby offers a gravitational nudge, a chance to tweak the trajectory, and, in theory, to set up a capture at perihelion if the timing and geometry align. For those tracing the boundary between natural and intentional, the flight path itself becomes a silent witness. The odds of such a corridor, low inclination, sequential planetary assists, perihelion blackout, stack up against every expectation from population models. The question lingers. Is Atlas simply the beneficiary of cosmic coincidence? Or is there something more at play in the architecture of its journey? Number 3. The statistical and population model anomalies surrounding 3I/Atlas strike at the foundation of how astronomers expect to discover interstellar visitors. Survey algorithms, deployed by Pan-STARRS, Atlas, and the Vera Rubin Observatory, operate on a simple premise: small objects vastly outnumber giants. The math is unforgiving. Power law distributions predict that for every Atlas-sized body, thousands of lesser fragments should have crossed our telescopes first. Yet the record shows the opposite. Instead of a slow buildup of detections, the surveys leap straight to a 20-kilometer nucleus, bypassing the expected parade of 1-kilometer and sub-kilometer interstellar objects. The odds of this sequence, under standard detection models, fall below 1 in 10,000. Internal memos from Rubin's analysis teams flagged the anomaly early, warning that either the algorithms are missing entire classes of objects, or that Atlas itself is a statistical outlier of staggering proportions. Detection pipelines, hardened by years of asteroid hunting, may harbor blind spots, hard-coded size thresholds, chemistry filters tuned to solar system norms, or selection biases against odd trajectories. Whistleblower reports from within the survey collaborations point to heated debates over whether to recalibrate these systems in light of Atlas's appearance. For population theorists, the anomaly is not a footnote, it's a crisis. If Atlas is truly representative, the cosmic inventory of interstellar wanderers needs rewriting. If it's an outlier, the burden falls on every future survey to prove that the next Atlas won't slip through the cracks. The numbers refuse to stay quiet, amplifying every other mystery in Atlas's dossier and setting the stage for the physical scale anomaly that follows. Number 2. Atlas's anomalous properties redefine the scale and inertia of interstellar visitors. The nucleus alone measures close to 20 kilometers across, a mountain of ice and rock that dwarfs every prior interstellar object ever recorded. For context, Oumuamua stretched less than a quarter kilometer, Borisov barely a single kilometer. Atlas towers above, its mass estimated at over 33 billion tons. That figure isn't speculative. It's derived from brightness measurements, corrected for distance and solar phase, then modeled against the most conservative comet reflectivity values. The result? A body so massive that even its own outgassing seems powerless against its trajectory. The numbers on gas production are equally staggering. Solar probe data confirm that Atlas emits between 100 and 150 kilograms of carbon dioxide every second. In comet science, this level of activity should act like a rocket, imparting measurable non-gravitational acceleration and nudging the nucleus off its predicted path. Yet the global data set, over 4,000 astrometric measurements, shows no such deviation. The upper limit on Atlas's acceleration is less than 15 meters per day squared. Take the measured gas production, multiply by outflow velocity, and divide by mass. The expected reactive kick simply vanishes unless the nucleus is not only large, but remarkably dense, or its jets are so perfectly balanced that every force cancels out. Monte Carlo simulations run by orbital dynamicists sweep through every plausible combination of size and density. Anything smaller than 5 kilometers across would have been blown off course long ago. Only a truly massive, possibly monolithic object could remain so unmoved. This inertia isn't just a curiosity. It magnifies the stakes of the coming blackout. If Atlas were to experience a sudden change in velocity or trajectory while hidden behind the sun, the sheer scale of the object means the consequences could be profound and the evidence invisible until it re-emerges. The physical enormity of Atlas is not just a statistical outlier. It is the single greatest amplifier of risk as the critical window approaches. And finally, in first place, the calendar delivers a moment of cosmic suspense that no simulation can resolve. October 29, 2025 draws a hard line across every observatory's schedule. On that day, 3I/Atlas slips behind the sun, vanishing into a 6-week blackout that coincides with its closest approach to our star. The geometry is merciless, Earth, Sun, and comet arranged so that every telescope, from mountaintop to orbit, is forced to stand down. Hubble and the James Webb Space Telescope normally the eyes of the cosmos, are locked out by safety protocols. Even the most determined astronomers must yield to the glare, their instruments at risk of destruction if they so much as glance toward the forbidden zone. This is not a routine conjunction. Perihelion, the instant when Atlas skims nearest the Sun and the laws of orbital mechanics reach their most volatile, unfolds in total darkness from Earth's perspective. For nearly 6 weeks, astrometric tracking, spectral analysis, and even basic photometry all fall silent. The world's greatest observatories are reduced to bystanders, unable to witness the very moment that could decide whether Atlas escapes to interstellar space or becomes a permanent resident of our solar system. Solar probes and coronagraphs, built to monitor solar storms and coronal mass ejections, offer only a faint hope. Their sensors, not designed for the subtle signatures of a distant comet, might catch a fleeting dust outburst or plasma trail, but the odds are slim. The Parker Solar Probe and Solar Orbiter teams scramble to reprogram exposure cycles, risking hardware to chase a ghost through the corona. Even Mars orbiters, momentarily well-positioned, face pointing constraints and limited time on target. For most, the window slams shut just as the story's most critical chapter begins. This blackout is not just a scheduling inconvenience. It is the ultimate test of human observation. If Atlas were to experience a sudden, decisive shift in velocity, a maneuver capable of flipping its path from escape to capture, every witness would be blind. The defining act, whether natural or artificial, would unfold in the one interval when no one can confirm or deny what happened. The suspense is total. Only when Atlas reemerges in December will the numbers reveal whether an irreversible change has occurred. Until then, the fate of the most massive interstellar visitor ever recorded hangs in the balance, hidden behind the Sun and beyond the reach of every eye on Earth. From the quiet anticipation of the next observation windows to the dramatic 6-week blackout at perihelion, this countdown has revealed just how unprecedented the Atlas is among interstellar visitors. The list's most shocking entries, Atlas's massive size, its ecliptic-hugging trajectory, and the statistical impossibility of its discovery, consistently challenge what we thought we knew about wandering objects from beyond our solar system. Patterns emerge. Every anomaly, from its carbon dioxide-rich chemistry to its engineered seeming path, stacks up to make Atlas a genuine cosmic outlier. What qualified each entry was its measurable defiance of normal comet expectations, culminating in the tense moment when we simply won't be able to watch what happens next. Together, these facts reinforce why experts like Michio Kaku argue that Atlas could rewrite the rules on interstellar objects. Whether Atlas is ultimately captured or sails on, its anomalies force us to rethink our place in a universe where even the rarest events can and do happen.